Hello, Math 157ers. This is Professor D, and we're going to talk now about Section 7.4, Estimating the Population Proportion with Confidence Intervals. Okay, a confidence interval for a population proportion is an interval where the unknown population proportion is likely to lie. Okay, so suppose the central limit theorem applies, and we want to estimate P, or the population proportion. The sample proportion is 0.24, and the standard error is calculated as 0.03. If we want to estimate 1.96 standard errors away from the mean, we take the sample proportion and subtract 1.96 times 0.03, and we'd also add 1.96 times 0.03. Remember, we're going to multiply. Order of operations says we do the multiplication first. Okay, so we could estimate this confidence interval to be between 0.19 and 0.3. Now, 1.96 translates to a 95% level of confidence. And what we can say is that if we took 100 confidence intervals, 95 of those would have the true population proportion in them, and 5 would not. We'll talk about where the 1.96 and 95% correlate in a minute. Okay. The proportion of green M&Ms is 0.16. You take several samples of 80 M&Ms each. So you're going to be doing several confidence intervals of 80 M&Ms each and come up with the following 95% confidence interval. Okay. Now, if we look here, all of the above confidence intervals except 0.11, 0.15 successfully contain the population proportion. Now, when we talk about this proportion of green M&Ms up here, we're talking about the true proportion. So M&Ms actually says 0.16, or 16% of our bags are going to be green M&Ms. That's the true population proportion. These numbers down below here are based on samples. So we take a sample of 80, and then we say, okay, how many of those are green? And then we come up with a proportion, and then we calculate the confidence interval. So like I said before, for every random sample that can be taken from a population, there corresponds a 95% confidence interval. And here, 95% of these confidence intervals will successfully contain the population proportion, the true population proportion, and 5% will not. Okay. Now, the 95% confidence interval, when they're talking about the 95% confidence interval, they're really talking about hitting 95% of the data inside a normal curve. So this area in here is 0.95. So the area and the two tails together is 0.05. So the area in each tail is 0.025. 0.025. This corresponds to a z-score of negative 1.96 and positive 1.96. That's where they keep multiplying the standard error by 1.96, because if we drew our normal curve, remember the total area in the normal curve is 1, 95% confidence intervals is that 95% of these confidence intervals are here. And we're also looking at the area in the tails, and this is where this 1.96 comes. It comes from the z-score. So 1.96 standard deviations below and 1.96 standard deviations above. And so let's see if I can get this off my screen. Sorry, I don't have a quick way of doing this. Maybe I do. Oh, I do. All right. So of 500 people surveyed, 72 were smokers. Find the 95% confidence interval. Well, the first thing we do is find the estimate. So this is sample estimate, 72 out of 500. Here's standard error of the estimate, so our proportion 0.144. Plug it in and we get that. Now remember, we also need to make sure that n times p, really p hat, is greater than or equal to 10, and n times 1 minus p hat is greater than or equal to 10. So this is from 7.3, so we have 500 times 0.144, and then 500 times 1 minus 0.144. We looked at our calculator, and we cleared this off. 500 times 0.144, that's going to be bigger than 10. And then I'm sure that 1 minus 0.144 times 500 is also greater than 10. And if you think of it, all of the, there are more than 500, there's more than 5,000. Remember, our little n times 10 has to be less than or equal to the true n. Well, if you think about it, 500 times 10 is only 5,000, and there are definitely more than 5,000 smokers out there. So let's erase this ink and keep working. So the margin of error is calculated by taking the standard error and multiplying by 1.96, which corresponds to a 95% confidence interval. So we subtract that from 0.144 and add that. So we can say with a 95% level of confidence that between 11.3 and 17.5% of all people are smokers. So if you sampled 100 people, you would think somewhere between 11 and 17 or 18 people in that group of 100 would be smokers. Okay. So if you look at confidence versus margin of error, let's get another slide. Okay. As I showed you in that illustration before, 95% level of confidence is about 2 standard deviations away from the mean. 99% level of confidence, because remember, 99% level of confidence, the area that we're covering is 0.99. So the area in the tails, 1.99, which equals 0.01. So the area in each tail is going to be half of that, which is 0.005. So that's why it's going to have a larger z, which is 2.58 standard deviations away from the mean. Pretty much 95% level of confidence is standard. If you want to have a smaller confidence interval, you could use a 90% level of confidence. If you want to have a larger confidence interval, you'd use a 99% level of confidence. So increasing the level of confidence increases the margin of error, while decreasing the level of confidence will decrease the margin of error. 176 of 200 patients randomly selected to receive treatment survived find the 90% confidence interval. So we find the proportion. Remember, we should take it through the central limit theorem test. I'm sure that the population of patients is more than 2,000, the total population, and I'm pretty confident 0.88 times 176 and 0.12 times 176 are both greater than 10. So you find your margin of error because for a 90% confidence interval, see the previous slide, it's 1.645 standard deviations away from the mean. We add and then we subtract. So we can say with a 90% level of confidence that between 84.2 and 91.8% of all people who receive this treatment survive. Now I'm going to show you inside StatCrunch. And slightly worried that it's not recording this, so application sharing. I'm going to turn it off for a second. Reshare. There we go. It's not in the yellow where it's not being shared. Stat. Proportion stats. One sample with summary. All right, so let's look here. 176 of 200. 176, that's the number of successes of 200 patients, 90% confidence interval. 176, 200, we're doing a confidence interval, 90%. You just leave the method as standard walled and hit compute. Sample proportion is 0.88. That's standard error, 0.02987. We can 0.023. So why are we a little bit off on our standard error, 0.88? Well, it's probably how they rounded. But if we look at our confidence interval, they said 0.842, 0.918, 0.842, 0.918. There you go, the lower limit and the upper limit. This is a little bit off. But StatCrunch will do it for you. You just have to know what everything means inside of StatCrunch. Come here to the next slide. 300 randomly chosen voters were asked if they favored the bond initiative to fund a new college sports arena. 120 did support it. So let's do the 95% confidence interval in StatCrunch. So again, I notoriously do this all the time. 120 out of 300, I mean 95% confidence interval. You can actually be lazy and just options edit. 120, 300, need a 95.9 confidence interval, compute, and I'm getting 0.344, 0.455, so about 34.4% to 45.5. Let's see if we agree. 0.34, 0.46. So here's the thing. A bond initiative requires more than half the population to vote for it. And since 0.5 is above the confidence interval, it's unlikely that that bond initiative is actually going to pass. All right, so StatCrunch and confidence interval, just like we did. Stat proportions, one sample with summary. You put the number of successes, number of observations, confidence level, hit calculate, and you have your lower limit and your upper limit. Okay, so you can use a confidence interval to give you plausible bounds on a population proportion. You have to check it with the central limit theorem. 95% is typically standard. 90% can be used if you need a smaller margin of error. And a higher level, 99% can be used at the expense of a higher margin. Okay. I'm going to do one quick problem. In 2000, problem 5. In 2003 study on dreaming, an investigator attempted to replicate an experiment by Middleton in 1942. In this study, 91 of 113 people said they dream in color. So if we want to find the proportion, 91 divided by 115.79, so we need this as a percentage, 79.1. To find the 95% confidence interval, we don't even need that because we can go right into StatCrunch. I wish I could split the screen, which actually I might be able to do. Oops, let's see if it'll work. There we go. Sort of a modified split screen here. If I do split the screen, it doesn't always work. Yep. Okay. Let's close this. Here's always no problem. You try and split a screen with here. Doesn't ever want to work the way you want it to work. All right. All right, so let's do a 95% confidence interval. Stat. Proportion stacks, one sample with summary. Number of successes, again, is 91. Put that in the wrong place. 91. Number of observations is 115. I'm going to do a confidence interval, 95%. I got to scroll over here. It's just not going to play nice with me, so I'm going to have to make this better. And I'm going to hit compute. So at lower limit 0.7170, so we can even just copy these numbers in. Control C. Now, be careful here because I'm putting in the decimals, but what does it really want? It really wants percentages. So I'm just going to go ahead and put in this raw data, round to one decimal place. So that's going to really give me 71.7%. And it's going to mark you wrong if you add all that extra stuff. And this is really going to be 86.6 is what I'm going to go with. And I'm worried about all this. My second answer is corrected, not like, oh, 71.7. I'll put 71.1. There you go. In this study from 1942, 29.24% of people reported dreaming in color. Does the data from the 2003 capture 29.24? No, because our data is 71 to about 86. Is 29.2 plausible as the 2003 population percentage? No. Okay, so the interval does not capture 29.42. So right away we can eliminate B and D. So let's look at A. The interval does not capture 29.24%. This shows that the results in 2003 were quite different from the results in 1942. The interval does not capture 29.24. This shows that the results in 2003 were quite similar. No. The only possible answer is A. And there you go. Well, I think you guys are ready, and I hope you enjoyed this lecture. Take care.